Okay, so we've just kind of gone through and we've spoken about how to calculate the specific heat capacity of things in the last video. We also briefly mentioned about converting between units of specific heat capacity. So again, if you haven't drawn this diagram in your book, can I get you to just jot this down somewhere real quick? We also talked about enthalpy changes and how it's kind of related to this idea of specific heat capacity, because even though specific heat capacity is looking at the ability of a substance to retain heat, and enthalpy changes are talking about the energy stored within bonds, we can actually sort of indirectly or directly measure them using the change in temperature. And we do that using a calorimeter. So like I said in the last one, you can actually make your own calorimeter at home using a couple of not environmentally friendly styrofoam cups, as well as a stirrer and just a thermometer. So for example, if you had some sort of assessment coming up where you maybe had to do some sort of student experiment and we're still stuck in Corona Town, then maybe this would be something that you could actually do at home. Interesting. All right, so one problem with this though, obviously because it's just like 2 coffee cups, and you know, like if you've ever had like a hot coffee, I always have black coffee, and if you ever go to a server or anything and you get black coffee, they don't put cold water or anything in it, and so it's always burning hot, and so they always give me 2 styrofoam cups or 2 cups. Most places actually give out paper cups now, so that we don't burn ourselves. But I can still feel the heat of the coffee through 2 of the cups. So it's not exactly the best system. There is a lot of energy that is lost to the environment. And so because of that, this particular experimental technique involves a lot of errors. So if you do decide that this is an experiment that you want to do at home or you want to do a report on in the future, just be aware of the fact that there is systematic errors associated with that. That doesn't mean that you can't do this experiment. You just need to make sure that you're talking about what those systematic errors are. Okay, so let's have a go at this particular question here. So when 3.85 grams of cesium fluoride is added to 40 mils of water in a coffee cup, a temperature rise of 5.4 K is measured. Calculate the enthalpy change for of solution for 1 mole of cesium fluoride. All right, so the first thing, why don't we calculate the energy absorbed by the water first? Now, the other thing is we are going to have to convert the cesium fluoride to moles, but we've done that a bunch of times. Let's do the energy absorbed by the water first. So we're going to use that formula that we were using previously. So the energy required in joules is going to be equal to the mass times by the specific heat capacity times by the change in temperature. Okay, so let's substitute in the values that we know. So what do we know? We have 40 mils of water. And so with water, remember the mass of water, 1 mil is equal to 1 gram. So that's a really nice, simple conversion because 40 mils is equal to 40 grams. So that's going to be 40. Now, the specific heat capacity of water was 4.2 joules per gram per Kelvin. And the temperature change mentioned in the question was 5.4 Kelvin. So if I just quickly chuck that in my calculator, 40 times by 4.2 times by 5.4 is going to be equal to 907.2 joules. All right, let's go ahead and let's convert this into moles now. So we have the mass of cesium fluoride is equal to 3.85 grams. I've actually gone ahead and I've worked out the molar mass off screen. So that's going to be 151.91 grams. Oops, got to put units, grams per mole. So to find the number of moles, all I'm going to do is divide the mass by the molar mass. So again, that just comes from that original formula that we've used a few times now, and I've just rearranged it, and now I'm just going to substitute those values in. So that's going to be 3.85 divided by 151.91. And again, let me just quickly chuck this in my calculator. So 3.85 divided by 151.91. And that's going to be equal to 0.253 moles. Okay, so next step. So we're going to use that formula we were just looking at before. So the change in enthalpy is going to be equal to the energy change. Now this one here is in kilojoules. So let's convert this quickly to kilojoules. So to do that, we're going to divide by 1,000, and that gives us 0.907 kilojoules. Okay, so, let's finish that formula off. Divided by the number of moles. So now all we have to do is just substitute into the equation 0.907 kilojoules divided by 0.253 moles. And again, let me just quickly check this in my calculator. 0.907 divided by our answer is equal to 3.58. I'm just going to round that just to 3 significant figures here. And that is going to be measured in kilojoules per mole. Okay, so what I want you to do now is I want you to have a go at this equation here. After the break, what I'm going to do is I'm going to come back and I'm going to show you the solution for this question. All right, again, I'm just going to show you this last little bit. So the change in enthalpy is going to be equal to the energy in kilojoules divided by the number of moles. Now, just to get this in kilojoules, I'm going to divide by 1,000, and that's going to give me 0.44. Let's round this up actually. Let's just round this up to 450. Okay, so kilojoules, units. So 0.450 kilojoules divided by 0.00486, and that's going to be equal to, let me just pop this in my calculator. I'm actually just going to chuck the original 449,565. I'm a little bit picky like that sometimes. And that's going to be equal to 92.60 kilojoules per mole. Okay, so that is our solution. How'd we go? Good? I hope so. If not, just send me another question and we can go through another example if you need. All right, so let's jump in. Let's have a look at this next sort of little section here. And this is sneaky, hinty, because for your assessment, what you're going to have to do is you're going to have to calculate some sort of enthalpy change in a combustion reaction or something like that. Or you're going to have to pick one of the other labs. And there's a bunch of labs that I'll talk about when we actually give out the assessment that you could do. And so what you have to do is you have to go, you pick your independent variable, you pick your dependent variable, you come up with a hypothesis based on that. So if such and such affects such and such, then I will see such and such take place, or however we want to do the hypothesis. And again, I'm going to speak a little bit more detail about how to do that properly when we actually come to doing our assessment lessons. Excuse me. But if we do end up having to do our assignments at home, I think this one would probably be the most effective one. If you have a thermometer at home and if you have stuff that you can light on fire at home. That being said, a little bit dangerous. Okay. So I'm just going to leave it at that. I'm not going to explain too much more details, but just to let you know that you could maybe do this at home if Corona does mess us up. Okay, and that was pretty much it. That's all we needed to do. So going through calculating the specific heat capacity using the mass, the energy, and the change in temperature. And then the other thing that we've done for this lesson is we've gone ahead and we've calculated the energy change, keeping in mind that the energy change we're talking about is related to the moles and kilojoules, and specific heat capacity is referring to grams and joules. So just be aware of those differences in the units. All right, guys, I will talk to you next time. Have a nice day, and I hopefully will get to see you guys soon. Bye.